嗯，啊，他懂，还有什么做 role reduction 就对了。Before we start, give you one question to think about. This question is given by one of your classmates. Maybe it's worth for you to think about as a warm up. Any idea? Edward? X equals to -1. Okay, so you will get maybe 11, 2 like that. Okay, so this is by what? By the definition of the coordinate basis. Okay, because the coordinate basis is exactly reading out the scalar, the scalar that you multiply to your basis from this linear combination. Okay, it tells you how you use the basis to write your x as a linear combination. Okay, but your classmate is very innovative. So the second question is, we use change of basis, or in your textbook, I recognize they use change of coordinate, right? Change of coordinate. Matrix. E, B to C, say. Of Q1, what do you think? we use change of basis matrix to solve on. Okay, why someone would think of this? Because what? Because you can think that x as a coordinate basis in terms of the standard basis. Okay, but you are given x in the basis b also. Okay, so the problem is, what is this pb to this standard basis here? How to find this? You know how to find this change of basis? I mean, this will be coming out in your quiz of how to build a change of basis matrix. How to form this matrix from B to this standard basis. How to find it? Huh? So, who says something? Who want to try? How to find? Let's write the B down first. Who want to try? How to find this change of basis matrix from B to C? What you need to form? What do you need to form? How to compute this? Anyone know how to compute this E from B to C? And what to do? You need to form a augmented matrix, right? Okay. So what do you put in your augmented matrix? Okay, you put C on the left hand side and then put B on the right hand side. And then you row reduce, right? Row reduce until what? You get identity on the left hand side. And then what's left over is your change of matrix basis. Change of basis matrix. Yeah. But in this case here, it is already identity, right? So your change of basis matrix is just one. Minus 2, 3, 1, 1. Okay. And then multiply on this coordinate basis. You should see that you get the same answer. You should get the same. Okay. So if you notice when you do this coordinate basis multiplication here, right, it's exactly what you do on this matrix multiplication. You notice? And row times column, row times column is exactly what this doing. Okay. You have minus 1 multiply on negative 2, also multiply on minus 1. Okay, and then you add to 3 times 3 on first row, 3 times 3 on first row, and 3 times 1 on the second row. Okay, it's the same calculation actually. Okay, no. Question for question? Okay, so if you notice in this tutorial question inside the textbook, right, there are several ways to do one question. Right, there are several ways. Okay, and as long as you are using definition or using right theorem, that's fine. Yeah, no. Yeah. But I encourage you to solve from definition first. Okay, and then learn what are the theorem can be used. For example, some of you asked me about the subspace question, right? So to check something is a subspace, you need to check the three things, correct or not? But in the textbook, they also teach you to prove from the point of span. Okay, if you know that span of a set of vector is always a subspace. And this is what we proved in class. So if you can show that your set is a span or something, then it is automatically a space. Okay, yeah. If you don't know, right, don't know any theorem, just go back to definition. Okay, always work from definition. Okay, so this question come up from your friend. Your friend are very worried. So she asked me about this question here, and then she mentioned something which I hit my heart. She said, 老师，我不懂诶，要帮讲讲啊，我不懂怎么做，我一直不理解，可以帮助我。我不要死记硬背，我不要死记硬背。他讲，我不要死记硬背。我讲，Yes，you are right，不要死记硬背。对啊，就是不要死记硬背。The max I teach is not about memorizing. Okay, so what's this 死记硬背? Maybe for some non-Chinese student, I write out this forward for you. 死记硬背. If you don't like a lecturer, right, just tell him or her 死记硬背. You can score them using this. 死记硬背. What is this 死记硬背? There's 4 words here. Okay, first is that 死. Okay, if you heard about 死, it's not a good one. It's that. Okay, 记 is learned by root. Okay, and then in is hard, and then pay is memorized. Okay, all those 4 bad words put together. Okay, why are they bad? Right. So why are they bad? Because if you are bad, you are not likely enough. Okay. So if you learn by root, you can't really apply. You cannot apply to other place. You can only apply to that question. Right? And why hard is not good? You think hard is good? Is hard good? Hard good or not? Okay, maybe someone think it's good. But why is it not good? Because not flexible enough. Okay. And why is it memorizing not good? You cannot generalize. You cannot generalize to different cases. Okay, more general cases. You just know, oh, that case use this, that case use that, that case use that. Understand or not? So the maths that I teach, that I teach to students is different from most of the maths student, a maths lecturer, I think, or teacher even. Okay, because most of the maths teacher might be teaching you solving question only. Okay, you just solve enough, you will know how to do. It's not very wrong, but they could be wrong in assessing students. Okay, because they just give the same question, and then the student will think that, oh, I know how to do, I know how to do. In fact, if I change a little bit, then the question, the student will go confused again. Okay, no? Yeah. Okay, I'm not saying that you don't do a lot of questions, but when you do these questions, right, you must make sure you understand what is happening. Okay, no? Yeah. Maybe in this GE you can still success, okay, through this 死记硬背. Okay, but in real life, right, it's very different. Real life is very, very different. Okay, because in real life gonna change. Okay, situation gonna change. Every day is changing. Does that make sense? Yeah, it's always changing. Okay, now. Okay, what's not changed is the principle. So you must hold on to the principle. In our case, what doesn't change? Definition. Definition won't change. Okay, so you must understand the definition very well. If you notice, whenever you ask me a question, right, I must ask you one. What's the definition of this word? For sure, you don't understand what's this definition. That's why you don't know how to do. Once you understand it, you will apply to different question type. Does it make sense? Okay. Yeah. Okay. Before we continue with diagonalization, I want to do some summary first. Okay, so let's say we want to steps to diagonalize by n matrix. Okay, so we diagonalize a square matrix here. So what's the first step we did? So the first step we did is to find the eigen values of A. Correct or not? Okay, we want to find the eigenvalues for A such that D is a diagonal. Okay, I cannot say such that. Just say to form diagonal matrix D with these entries being the eigenvalues. Okay. Okay. And then, right. So what am I doing here? If you forgot what does diagonalization means here, we want to write A equals to what? PD, P inverse. Okay, such that D is a diagonal matrix and P is invertible. Why invertible? Because you need its inverse. Okay, okay, so to find D, you need to find the eigenvalues of A. To find P, you need to find the eigenvector. Okay, you need to find the eigenvector of A. To form the columns of. Okay, so a question, I think after the class, right, someone asked me how to arrange, right? You see, you have a diagonal matrix here. You have eigenvalues here. How to arrange, which eigenvalues come first? What do you think? Which one comes first? Huh? Any, but it depends on what? Combination. Which vector combination? Depend on how you arrange the eigenvector in P. Okay, so if your P, or for example, so if your P is like V1, V2, up to Vn, right? Then your D should follow the eigenvalues of the eigenvector correspondingly. So meaning first column here correspond to lambda 1, second one correspond to lambda 2. Okay. But actually, you should ask the question, why on earth, if I put all the eigenvector together, then this guy should be invertible one. Why? Why I just put all the eigenvector together, then they are linearly independent. Why? Because this is an algorithm, algorithm, right? So this means that this algorithm always works. Always work. What facts you need to know? To say that this matrix here is invertible, right? Is equivalent to say that these columns are linearly independent. So you need a statement to tell you that eigenvectors are linearly independent. But what's the statement? What's the correct statement there? You still remember? Do you still remember or not? What's the correct statement? Eigenvectors different, not from, for. Eigenvector for different eigenvalues are linearly independent. Okay or not? Okay, eigenvectors for different eigenvalues are linearly independent. Remember last time we discussed about this? Within the same eigenvalue, the eigenvector should be linearly independent. Why? Because it span a null space. Okay, now this one is combined all the eigenvector together correspond to the same matrix. Still linearly independent. Okay, still linearly independent. Okay, but the question here is, what if I repeated my eigenvalues? What if I repeated eigenvalues here? Sorry, please answer one thing. What if I repeated eigenvalue? Okay, so maybe, for example, the case 110. This is still diagonalizable. Okay, so I mean, because we say that different eigenvalues, their eigenvectors are linearly independent. But let's say we have, so let's say there are three possible eigenvalues, right? But two of them are the same. Is it always diagonalizable or not? Okay, actually the problem is, so let me put here. So there are two cases here. Two cases here. Case A, case B. If all lambda i's are different, then you will have n linear independent eigenvector, which implies that A is diagonalizable. But if if some AI repeat, sorry, not AI, lambda I repeat, then A may not be diagonalizable. Can you think of why? The answer is multiplicity. Why? Not diagonalizable meaning you don't have enough linearly independent vector to build your P. Why you don't have enough? There are two types of multiplicity we mentioned about right last time. What's the two types? Algebraic and geometric. Okay, so algebraic tells you how many times lambda i's appear, but geometric says what? The dimension of null space of A minus lambda I, or the dimension of the eigenspace for lambda I. So you could have less multiplicity than algebraic multiplicity, such that you don't have enough linearly independent vectors. Okay, so now we will do two examples. Okay, now we will do two examples. One example is you have repeated eigenvalues, but because algebraic multiplicity equals to geometric multiplicity, so that you have enough linearly independent vector. Second case is you have repeated eigenvalue, but the geometric multiplicity is less than algebraic multiplicity, so that you cannot form this here. Okay, so let's try these two examples now. Okay, let's try this example first. So I give you 2 minutes, 3 minutes like that to find the P and D together. P and D. Yeah, find the P and D. So I'll try and diagonalize this matrix. I follow the step I showed you just now. You can try and find P and D. Please take this time to practice because I know you go back, maybe not studying. So please try to compute. Now we can check solution together also. Okay, so let's go through together. So the first thing, if you want to find this eigenvalue, right, what do you look at? You look at the determinant, the characteristic polynomial, right? Now, then you look for this characteristic polynomial. Okay, so if you find this, should we go through this? Okay, let me at least write down the form first. Okay, so you can see that if you do any core factor expansion, it could be tedious, right? So maybe you want to do some row reduction in middle. Okay, so at the end, you're gonna get minus lambda minus 1 times lambda minus plus 2 squared. Okay, should we go through this calculation on finding the determinant? Are you okay? You want to go through together? Yeah, you want to go through? Okay, let's go through together. Okay, so what's the first thing I'm gonna do? What do you think? Should I go first? How about making a pivot first? Let's make a pivot. If I divide the first row by 1 over minus lambda, what I get is 1, 3 over 1 minus lambda. No go around with this one, so let's do this first. Okay, but if we do this, what's the effect on the new determinant? What's the effect if you scale the row? You also scale the determinant. Okay, do you scale the determinant by the same factor or not? The same factor? I remember. If cannot remember, please go and check. Do we scale with the same factor or not? Do we scale with the same factor? Should I also check? Let's check. Should find. Enter 6. Venture 6. Okay, here. Okay, so if you scale by a row, okay, you also scale the determinant by the same factor. Okay, if you scale by R, your effect is also multiplied by R. Okay, okay, okay. But if you do row replacement, you will do nothing. Multiply by 1. Okay. Understand? Can follow? Okay. So what we're gonna do next is we're gonna uh, do. Okay, so let's replace both row. So replacing row is just multiplied by 1, right? So we don't really care about the change of the determinant because it doesn't change. We care about it, it doesn't change. Right. So if we do this, what do we get? So obviously we're gonna make the first column 0 below the pivot position. How about the other term here? Is it messy or not? Maybe just write it out first. Minus 5 minus lambda plus 9 over 1 minus lambda. And then minus 3 plus 9 over minus lambda. And then 3. So here we should use minus instead. So 3 minus 9 over 1 minus lambda. And then 1 minus lambda minus 9 over Okay. Are we ready to compute this? Can we compute this? I think it's enough already, right? We can straight away compute, right? If we expand on the first column. Correct or not? Any calculation error? Any calculation error here? Or error or not? Any error so far? If got error, let me know. Okay. If not, we just continue. So if we expand on the first column, right, you should get 1 times the this minor here, correct? Okay. Then you need to expand this already. What's this? See. If any calculation error, please let me know. This 1 over 1 minus lambda quite confusing. Can we pull this 1 minus lambda out? This out, I get 1 minus 5. Okay, let me think. Correct, right? So I can pull this out. Okay, well, I mean, no need to pull out first. Just multiply it. AD minus BC, right? Huh? AD minus BC. Okay. Okay, so what should we do next? Can I pull this 1 minus lambda square out such that I get it's 9? Oh, not just one is enough. I need to pull 2 of them out. Here for 1 minus lambda square. And here become 3 minus 3 times 1 minus lambda. It's 9 square. No, sorry, minus 9. So far, okay. Everyone do this, okay? So keep expanding this. So what should we get here? Gonna be messy or not? Let me see. Be messy. This is a mechanism, right? It's a primer for computer when to avoid this like the textbook say need to use computer. So we expand this. Is there any easy way to see it or not? Have you guys compute this? No. Then how you get answer? You stuck. You stuck. Can I see how you stuck? Let's see how you stuck. Anyone stuck? Can I see how you stuck? Oh, you use the 3 by 3 formula, is it? Oh, you use the 3 by 2. Okay, you use the 3 by 2 formula. How about you guys? Have you guys tried? Huh? Try. What do you do? See? Oh, you delete already. What else? You try 了？圆圆哈，是圆圆嘛？啊，你是 OK？Have you tried？See？你也没解出来。这个你听了，就是这个啊。哦，OK，看一下你做吗？做到这里是我做的。OK，看一下你们呢？你们做了什么？这是我做还是你做的？还是你做的？跟我差不多了。你呢？差不多一样。好，你呢你有做吗？都差不多一样。How about you guys？啊？Oh, like the expansion. So you managed to expand everything up? Oh, 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 seems like this one is it? No way. You no, yeah, let me check. Oh, in this case, this one is easier, right? You get the right polynomial, right? Okay. Okay, good. Very good. Okay, I think in this case, this is not very good. This is not a very nice way to proceed. Actually, the traditional way is easier. So this one you can try. Maybe you can very good. Try, but not good. Okay, but I think Nicole try a better way. So just straight away expand it. So to expand it. So you just expand along the first column here. So instead, you should get 1 minus lambda of the minor 5 minus lambda minus 5, 1 minus lambda. And then, so if you expand along the first column, so the signature for the first term is plus, second term should be minus. It's 3 times the minor 3, 3, 3, 1 minus lambda, and then plus 3 times 3, 3 minus 5. Okay, I think you use this. This one is easier to copy. Not many lambda coming up. Okay. I think it also works out, but it's just very tedious if you use the elementary matrix. Okay. Okay. Can or not? This one happy or not? Can accept? Use this one. Yeah, just use the normal definition. Okay. What's your name? The green guy. What's your name? Huh? Sorry, huh? Okay, can you use this? You will try? Okay. Is it more believable use this to get the solution? What did you do? See? Let me see. 啊哈，很错，有开车。那你算什么东西？会啊，应该不会啊，很正常，这个是很正常，这很正常。刚才那个我们就很多东西啊，耶，看那个，嗯，我觉得应该是的，因为答案是这个。哎，哦，maybe 少了一个吧，我觉得可能。OK，不要紧，等下我们讨论看。OK，but let's use this first. This one I think you can do, but I mean maybe a bit tedious. Okay. Once we get this right, so what do you do next? You need to find the eigenvector. Okay, so you need to find eigenvector for both cases. So let's say this is the first step. So second step, you need to find your eigenvector for two of the group. Okay, so you need to solve a minus I and a minus 2i, so become 2i. Okay. So two of these is what? Okay, I think I can see properly. 0, 3, 3, minus 3, minus 6, minus 3, 3, 3, 0. And then plus 2 become 3, 3, 3, minus 3, plus 2, so become minus 3, minus 3, 3, 3. Okay. Hey, can you see that in this kind of question, your matrix become more regular? Right? What do I mean by more regular? So it's like when you do row reduction, right? It looks easier. Okay, the previous matrix has some, I would like to say, extra stuff. Extra stuff. Okay, extra stuff. Correct or not? What's the original matrix A? So this is how I see them. How I see this eigenvalue here. Okay, so you can think of the diagonal terms is like the extra stuff. Okay, although actually this matrix is quite not symmetric. It's not symmetric, but okay. Symmetry have a meaning in linear algebra, but there's a symmetry inside here, right? So if you split in the middle, right, you can see that they how to split. Okay, how to split also not very good. Well, I mean, you can see some. Okay, one thing you observe here is you can see that the numbers appear in pairs except -5. Okay, that's all. Okay, but after taking the difference between scalar of identity, you can see that the matrix how looks even simplified. Okay, more simplified. Okay, such that when you do this row reduction, what do you get here? Okay, so what do you get for row reduction? Can I guess solution from the solution here? Should have 1, 1, 0, 0, 1, 0. Let me see. It's only one solution, so let me guess. What's the solution here? This one, this one. So I guess this matrix from the solution. Let's see. So not correct. So I try to do backward thinking. So let me see. So put the solution here first. So lambda equals to span of 1 minus 1, 1. Where do you think the solution come from? What do you think? How should the matrix look like to get the solution? Backward thinking. How? 1, 0, minus 1. Oh, put a minus 1 here instead. Okay. And then 0, 1, 0. 0, 1, 1. Hmm. Okay. I think this one makes sense. So if I read this, right? If I read the solution, what do I get? X1, X2, X3 should be equals to X3, X3, 3, right? So 1 minus 1, 1, good. Yeah, I think this one works. So what I want you to check is whether you get the step or not. Let's try the step here. And in the exam, you must write down what's your row reduction. Don't draw this for me only. Please write down the step. Okay, otherwise I cannot check your step, your solution wrong, then I don't know what step you use. Correct or not? Right, so make sure you write down the step. Okay. Otherwise, if your final solution wrong, I don't know where you come from. Then I cannot check. I cannot give you step marks. Correct or not? So make sure you write down. So if you don't do it in quiz, I will penalize you 1 mark. Okay, if you don't write down the step. Okay. For the second one, we play the same game. So yeah. Space is a span of two things. -1, 1, 0, and then -1, 0. Okay. Okay, so I play the same game here. So what's this? So let's guess this form here. So there are two variables, right? So it should be like two free variables. So it should be 2, 0 rows. And then how to get this -1 here? Huh? 1, 1, 1, 1, 1, 1, 1, 1, 1. Huh? Say again. Row 3, column 3. Uh-huh. Oh, okay, thank you, thank you, thank you. Oh, you mean this one. So 1 plus 2 is 3. Okay, thank you. Okay, okay, yeah, sure. Okay, yeah. So try and fill this row reduction in. Okay, so what did you see here? So in this case here, what can you take as your P? A equals to P, D, P inverse here. So how do you put your P here? So you have 3 vectors, right? So you put for the lambda 1 first, and then you put for the lambda 2. And then D, how do you put for D? So the diagonal term should be correspond to the eigenvector with the right column. So the first column is for 1, so you put 1. Second column is -2, the column. Okay. Should you find P inverse? No need. No need to find P inverse. Okay. But let's say if you want to check, how do you check? What do you think? How to check whether this is correct or not without finding P inverse? How do you check? Without finding P inverse, how do you check this equation here? Sorry? Huh? So you checking this is equivalent to check AP equals to PD. Okay. Without finding P inverse, you can check. Okay. I mean, you can find P inverse, but take a lot of time. If 2 by 2 still okay, 3 by 3, then you need the parameter state and join matrix. But that will be in your quiz. So I'm sure you learn. Okay. Yeah. So if you imagine if you swap the position of the eigenvector, you should swap the position of your eigenvalues. Okay, so the column of this eigenvalue depend on how you put their eigenvector. Okay. Yeah. Does it make sense? Okay. Okay. So you can see that the algebraic multiplicity of -2 is 2, and the geometric multiplicity of -2 is also 2 in this case. Okay. Okay, let's do one more. What time is it? Okay, let's do one more before we break. So let's straight away tell you the eigenvector, and then I want you to compute the algebraic multiplicity. So I straight away tell you this, the characteristic polynomial. You can go back and test it out. Okay, so one is again, one is -2. So now I want you to find out what's these what their eigenspace. So let's do it. Okay, so it's the first option here. Okay, if not wrong, you can check. Actually, you should get the same one. Okay, if you're not wrong, you should row reduce to this two. I'll give you time to do row reduction. Okay, so try and verify if you get these two earlier. I think the second one is easy to see, right? Get rid of one row using the other. And then the difference between these, the other two row is correct. 1 minus 1. Yeah, so it should be 1 here. Okay, yeah. So the difference between that is 1. Okay. Anyone finish? Finish? Correct? You check this solution. Okay. Can both or can? You check both? Okay. So if you're gonna form your P, right? Okay. If you're gonna form your P, I mean form your D. D is what? D is let's say 1, -2, -2, right? So our algebraic multiplicity is 2. But if you try to form your P, your P only have 2 linearly independent vector here. So not enough. Again, not enough to form your uh, diagonalization. Okay, it's not enough. Okay, so there's nothing. Okay, so I would say that since the geometric simplicity of lambda equals to -2 is less than its algebraic multiplicity. Oh, A is not diagonalizable. Okay. If you have all different eigenvalues, it's always diagonalizable because you already have n different eigenvalues, n different eigenvectors must be linearly independent. Okay, but here, if you repeat, okay, you need to make sure that the repeated eigenvalue should have enough linearly independent vector. But you can see that in this case here, the dimension of eigenspace is not equal to the algebraic multiplicity. Okay, it's possible to happen. We already give you an example. Okay, so you need to be careful when we're gonna diagonalize a matrix using repeated eigenvalue. If the eigenvalues don't repeat, for sure you can diagonalize one. Okay, yeah. If it repeats, then you will have a risk that the geometric multiplicity is less than the algebraic multiplicity. You see 2 here, or 2 negative 2, but only one dimension. Okay, so you need to be careful. I think this is the only thing you need to remember from this diagonalizable chapter here. So theorem here is this. Okay, so the dimension of an eigenspace for the eigenvalue is less than or equal to the algebraic multiplicity. So you can only be less than equal. So if your algebraic multiplicity is 2, if you found the dimension is 3, you need to be careful. It's wrong. It cannot be more than your algebraic multiplicity. And then A is diagonalizable if and only if the geometric multiplicity of each eigenvalues equal to the algebraic multiplicity. Okay, so that you have enough. Okay, you have enough eigenvector, linearly independent eigenvector to build your P. Okay, so far, any question? Okay, so if no question, let's take a break until 4:13. Take a break, okay.
就是你们在这儿的时候，就不是我就只说它这个变化，就它不是里面除以了1减 lambda 嘛，
对，
所以就变成了1减 lambda 分之一。我觉得应该是乘一个1减 lambda，因为它里面不应该是原来是3吗？它是 e 是1减 lambda 乘 a 的形式，然后你把这个1减 lambda 提出来，所以里面变成了3比上1减 lambda，所以外面不应该是1减 lambda。
等一下哈，
你明白
我在做吗？等一下我在做吗？我不是除 e over lambda。
对啊，除以1 over lambda 呀。
对，但是如果除的话，我不是这个 r 就是 e over 1减 lambda。
我的意思是，它比如说，如果说原来，比如说 a 它原来的 determinate 是 e 的话，对吧？然后我的 a 如果 scale 了 r 的话，那它的 determinate 不就变成了 r e 了吗？但是如果我从 r e 如果想求到 a 的 determinate 的话，我就如果想求回来，不是还是要乘2分之一吗？就像
你给我想想。
OK， 没问题。
对，好像有这一层关系，给我想想。有想想，好像有这一层关系，可以给我写一下吗？
啊，可以，没问题。
我是用反了是吗？
我觉得是有一点反。
OK， 好，给我 try 一下。假设我记录是1减 lambda a，sorry，
或者可以用一个其他的常数，也可以，比如说乘2或乘3。
对，没有错。想下这一个才是我们的这个东西，然后我们要放回去用。这你讲的是对的，给我想一下，因为本来应该是说我把1over lambda这边，然后但是我们刚才这个是这个就是 OK， 我应该知道你讲的对，我觉得我反了，我觉得你对，我觉得对，因为这个1减 lambda 应该是乘在这一边的，
乘在这一边
所以过来就变反。
对，因为它是左边的 就是左边的从原来的变成它除以1点兰姆达，所以我如果想那个新的返回去的话，就要乘
没错。OK，等一下我说一说。OK，谢谢。
还有一个这个地方还是有点，哎，不是这个。这个地方，我想知道这个 diagonal matrix 是怎么来的。我明白，就是上节课这样子的。
对。
这个时候，比如说这样子的话，因为它不是00嘛，所以你就直接找这个对角线，就是0、5、-2，剩下都是00。
怎么来的？是这个来的。这里告诉你有什么东西。
这里告诉我有什么东西。
对。
根据这个 eigenvalue 求出来这个
characteristic polynomial。characteristic polynomial 就这个东西。
所以如果说，还有上面有一个题，上面这个题的话，如果他问我的那个，如果这个题他问我的话，也是这个是吗？就他的叫什么 diagonal side 里的 D 的话，就应该是还是这个，哎，还是这个数，就是1-2-2，它对角线还是1-2-2，就它的 D 和这个 D 是一样的数。
对。
然后根据这个 eigenvalue。
对哦，是哦，这么我写漏掉啊？sorry 啊。对。为什么没有写出来？对。
我一开始以为是看那个 A 的对角线，
我忘记我写漏，下次你提醒我一下。如果你看我写这样的东西，不是，我写漏一个东西，你要告诉我一下，可能我就是，我写在这里，sorry，我写在这里，这里，I mean，
明白了。
因为你抄了哦，因为为什么我强调这个 P 啊？是因为这里有一个 P inverse 嘛，我怕你不知道谁是 P，所以我就强调一下 P。其实我是打算把他们3个写出来，把 anyway 这样子写应该是会比较好。
知道怎么找，我一开始不太知道怎么找 D，你现在
OK 好，
谢谢老师。
我有个问题，如果我们直接把这个 D 减2给提出来的话，
对，
要不要说2打不等于1啊？
想一下哦，确实是要，然后为什么你要做这一步呢？
那你提出一个所有数都除以一个等于0的数的话，不就不对了？
对，你对呀，然后
那我们是分情况讨论，就在这么说。
我是说，
一种情况直接说2打等于1，它直接等于1；一种
对，
打不等于1，所以说这个或者是2打等于。
我觉得你对，确实，等一下，等一下，
就是分2种情况。
对，比较严谨要这样做啊，比较严谨要这样做，对你讲的对，
应该没有问题。
OK 好，对，你是什么系的？你是会计，可以转来读数学。 Yeah. Okay, so before we continue for next part, so here, right, should it be 1 over 1 minus lambda or 1 minus lambda? Okay, so we need to think about it from the definition, sorry, from the theorem again. So the theorem is determinant E times determinant A equals to a determinant of E. Okay, so we need to think about which one correspond to EA, which one correspond to A, which one correspond to E. Okay, so E is what we do as our elementary row operation here. And the A should be the A minus lambda I here, correct or not? Okay, and then what we written on the right hand side here is the new EA. Okay, so in this case here, determinant EA will get moved to the right hand side. Okay, so in determinant EA, it should be 1 over 1 minus lambda. So in this case, if you move to the right hand side, this will become 1 minus lambda instead. Okay, yeah. So if you replace everything with 1 minus lambda I, then you will successfully reduce one of the power. And then I'm not sure if it's workable. Is it better? Maybe it look closer to the solution because we haven't expanded yet. Yeah, we should expand it. If you expand it, what degree you should expect here? What's the largest degree you should see? You should see degree 4, right? Because here got lambda square already. And then lambda square times something square again. So you should have lambda 4. And then here only have 3 lambda, right? 3 degree. So you should expect one of the degree get cancelled by 1 minus lambda. Yeah. If you go down this road. Okay. And then this 1 minus lambda also suggesting you that if you expand the whole thing up, you should have 1 as your root also, so that you can pull up this 1 minus lambda. Okay. Yeah. Any questions so far? So far, any questions? Okay. If you don't like this method, you also can just straight away do your cofactor expansion. Some of you use the 3 by 3 matrix definition. You can learn it. Try not to use it in your exam. Try not to use it. Yeah, okay. If you use it and then your answer is wrong, I don't think I'll give you any mark. Because we never teach that before. Unless we prove that formula from the cofactor expansion. Yeah, unless we prove it. Otherwise, please don't use the 3 by 3 formula. Anyone know what am I talking about? That if you look at your textbook or the previous note, you will see a 3 by 3 method to compute the determinant. It's like the 2 by 2 case. The 2 by 2 case will tell you use AD minus BC, right? And then the 3 by 3 will tell you some other method. You can learn it, okay, but please don't use it in the exam. Try not to. Okay? Yeah. Okay. All right. So next chapter. I think next chapter is the most abstract chapter in this course. I hope you can get it. I hope I can say it well. It's the most abstract chapter. Okay, after this section is chapter 6. Chapter 6 will be more geometric and not too hard, I think. But I think this is the most abstract chapter among all the section you see. Okay, let's see how to motivate this linear transformation. So we have V, okay, we have W. Okay, so these are two vector spaces. So we want to say that V has a dimension n and W have a dimension m. So can anyone tell me what does this two dimension implies? Dimension means what? Sorry? Number of base. Okay, so the number of vector inside the bases. Okay, so in other words, we can write V as a span of V1 up to Vn. So there are n vectors here. W, how many bases? W1 up to Wn. Okay, very good. Okay, but last time we have another arrow, right? We can go from finite dimensional vector to where? Rn. Okay, one is Rn, one is Rn. What's the map called? What do we use here? What's the map we call here? Okay, maybe I give a name, right? So here is a span of a set. Let's say this set is B, and then the other is span of C. Okay, so what's the blue arrow here? How do we go to Rn? Still remember the unique representation theorem. What's the mapping here? Start with a C. Huh? Coordinate mapping here. Okay, so we put a coordinate vector mapping here. So one is represented by B, one is represented by C. So what do we do here? What do we read out from this coordinate vector here? We read out the scalar. Still remember? We read out the scalar. Okay, so in the first case, we have V, and then V, we do the coordinate mapping here. Okay, which is the scalar. Okay, sorry. We applied it on V. And then we have a scalar, say C1 up to Cn. How to obtain this? Because we say that there's a unique way to write V in terms of the basis. Okay, so this is exactly how we pick out the n numbers out. Okay, it's a scalar. Does it make sense? Make sense so far? Okay, we play the same game to W. We play the same game to W. So we also can write W, okay, in terms of a linear combination of the bases, such that we associate this W to m numbers. Let's say D1, D2 up to Dn. Okay. So what's this middle arrow here? How do I connect two vector space? How do I connect two vector space? Last time I think we briefly talked about it. Start with L. Linear transformation. Okay, so we have a linear transformation. Say T. Okay, linear transformation. Still remember what's linear transformation? What's linear transformation? I would function such that it preserve addition and preserve scalar multiplication. That's all. Okay, just do these two things only. So you see, what do you think you need to fill in this picture? What do you think you need to fill in this picture? There's one place you need to fill in. Now, what do you think? You almost form a cycle already. How to form a cycle? You close it here. Close it here. Do we have this? What do you think? Do we have this? And you are building bridge between these four things. Do you have this or not? If we have, how to do it? Sorry, I try. Try. You have to go from here to here, right? So you need to give me a way. I give you 3 rows already. You just need to find me this row. Can you do it? Using this 3 way here. Well, you can compose these two together, right? But the problem is, this arrow is coming down. Is there a way to make it up? Make it out? Can reverse? Can? You think so? How? Can you make it out? Make it out means what? You need a map going from Rn to V. So meaning is like, do you have an inverse for this map or not? inverse. You understand what's inverse? Last time we talked about inverse, right? So let's say T inverse equals to the identity, right? So, all right, so let's do the other way. What does the inverse do? So let's say T is going from V to W, and then T inverse should go from W to V, so that your identity function is going from V to V. Okay. So can you go backward or not? So inverse is one way for you to go backward. So if you have map from V to W, the inverse will send W back to V. Okay. We do have an inverse here. Okay, so we do have an inverse. Actually, we do have this inverse here. Let me draw it. Okay. So we do have this inverse. Use source color, use this color. So we have inverse of the coordinate basis. Okay, so why? Because it is 1 to 1 and on 2. Okay, maybe I won't show you why on to 1 and on 2 will imply has inverse, but I will tell you this fact here because you know that. Because last time we mentioned, or I leave the proof for you that this is 1 to 1 on 2, so it's bijective. If you learn discrete math, you know, if you have 1 to 1 on 2 is bijective, then you will find the inverse. Okay, so meaning you can go backward. Okay, if you have a map that's 1 to 1 and on 2, then you can go backwards. Okay, I mean, very conceptually thinking is like this. Okay, conceptual thinking is this. If you have a 1 to 1 on 2 map here, it will look something like this. Okay, you can hit every guy in the codomain, and then when you hit the opposite element, you will have only one pre-image. It's 1 to 1. So how to make the inverse map? You just literally swap the arrow. Yeah, just send back where you come from. And just send back where you come from. Okay, this is your inverse. Okay, so this map, the down map here is actually go from Rn back to V and then go to W. So this is depending on T and then go to Rn. Does it make sense? Okay, no? Okay. So but what's the special things about here? What's the special things about here? Do you still remember? If this is a linear transformation between Rn and Rm, what is it? Actually, it is a, I want to guess. Standard basis matrix. The basis matrix. Depends 差不多, but actually I want to say is actually is a matrix transformation here. Okay. So meaning what? Meaning what? Meaning every T, right? Every T between vector space, right? You can correspond to some matrix transformation between Rn and Rm. And then how to decide this N and M depend on the dimension of your V and W. Okay. So again, we turn the question on the abstract vector space to matrix problem. Okay, if you want to look at linear transformation between finite dimensional vector space, actually again still some matrix multiplication only. Okay, but matrix multiplication on what? On your scalar. Okay, on your scalar only. Okay, so we don't need to remember V1, V2, Vn actually. Okay, but if you know how to add on scalar, can you go back to V or not? This is the first question I asked in the class right just now. If I give you coordinate vector, can you go back to your vector? Can, right? You just then multiply out your linear combination. So this is actually the reverse arrow. Correct? No? I give you all these coefficient. Find x for me. Okay, find the v for me. Then you just write down the linear combination. Okay, the problem is that there's a theorem saying that this is unique. So there's one way. So you just only correspond to one v. Okay, does it make sense? Okay, so if you go down, you take coefficient, you go back, put back the coefficient, okay, into the linear combination. Then you can find it. It's unique because the theorem says unique representation. Okay. Okay. Okay, so let's try examples. Let's try examples. Okay, let's try examples here. Okay, maybe look at the definition first. So if V and W is a vector space of dimension n and m, and then let B and C be bases for V and W. If T is a map from V to W, then there is this matrix. Okay, the size even they tell you already is m times n. Okay, m times n, where m is the dimension of the codomain, n is the dimension of the domain. It makes sense, right? Because this matrix need to eat some vector in n dimension first, and then give you a m dimension basis. So it makes sense. Okay, m times n, and then they write it in this way. Okay. You see that this small equation here actually come from this square. Right, right. Then you put x b here, and then you multiply, you get something in. Sorry, here is in C. So here is in C. Okay, let me demonstrate this equation for you. So if you eat the x, so I put x here, x can go to tx first. Okay, x go to tx. And then tx, you take your coordinate basis. So you get txc, okay? And then you have your x going to xb. And then how to go forward here is some matrix put inside here. Okay, you need to figure out what's the matrix. Okay, make sense? Okay, so this equation here comes from this square here. Okay, so let's try and figure out what's this question asking. So suppose B is a basis for V, and then C is a basis for W. So in this case here, V is dimension what? What's the dimension of V? What's the dimension of V? 2, okay. W dimension is 3, good. So let's T be a linear transformation such that this is true. So then we want to find this relative basis. Okay. So how do we do this? Should I use my method or not? Or straight away give you answer? Can I show you why is it true? Can I use my method? Let me think. Okay, so how about use the method I discussed just now. So let's start with so let's draw my diagram. Okay, draw my diagram. I think I want to teach you this very advanced stuff. This maybe not even MAT nor this. Okay, so we're gonna find this M here. All right. Okay, this is my goal. Okay, so let's write down what we have. So V is a span of B1, B2, and then W is a span of C1, C2, C3. Okay. Okay. Right. So we're gonna know what happens to M. Okay. So still remember, if we want to figure out linear transformation between two vector space, what do we need to check? Do you still remember? What do we need to check? M is equal what? Okay, before that, R2, what's the standard basis? Spanned by E1 and E2. And then R3, spanned by E1, E2, E3. But note that here the E1, E2 are different from the R2, E1, E2 because E1 in R2 is just 2 components here, but R3 have 3 components. Okay? Although we just use EI for every dimension. Still remember or not how to find a linear transformation between two Rn? Do you remember? Can I show you? So let's go back. Every time you don't know, you must go back and check the notes. Don't just use thinking. Okay, so here. Okay, so if you have a linear transformation between two Rn and Rm, right? Then your matrix, how to figure out? You just apply on EI. Just check what happened to EI. And then put their column together. Make sense? Okay, so what we're gonna do here is the same. So if we're gonna figure out what is M here, we need to know what does M do to E1 and what does M do to E2. Okay, okay, makes sense. Okay, so the problem is what does M do? But remember how we define this M? We define as, okay, so we should write down what is M is. On the other hand, not on the other hand, right? Okay, maybe on the other hand. On the other hand, M is what? M is equals to this, okay, can we give a name? Yes. So this one inverse times T and this. Okay, so this is the arrow here. So we're going backward on this, and then going forward, use T, and then going forward again. All right? Can follow? Okay. Okay. Question, go question or not? Please ask I go question. Okay, can follow? Okay. So we're gonna check this on E1 and E2. Okay, we're gonna check this on E1 and E2. So we applied it on E1. So we apply it on E1 first. Okay. So we apply it on E1. So you look at here. Where should this E1 go? E1 should go to where? Go to what elements here? Let's call it X. X equals to what? 1 times B1 plus 0 times B2. Correct or not? Because all the vectors here will represent the scalar unit for the linear combination. Does it make sense? You heard him? Okay. So actually, you send 1, 0 to B1. Then you send 1, 0 to B1. And then where should B1 go? So in this case here, you get B1. This definition tells you where B1 goes. Okay, B1 goes to where? 3C1 minus 2C2 plus 5C3. Okay, so let's do step by step. So if I apply the coordinate basis, coordinate vector on E1, I should get B1. But if I apply T on B1, is what question gave me here. So it gets sent to C3C1 minus 2C2 plus 5C3. Okay, but if you apply coordinate vector with respect to C on this, what do you get? You just read the scalar again. Okay, if you read the scalar, what happens? It becomes 3 minus 2 and 5. Okay. Correct or not? Size correct or not? Correct, right? R3. Size already correct. And then what's next? Check M on E2. Similarly. Okay, so you need to check on ME2. Okay, if you check on ME2, where should E2 go? 0 times, sorry, what is E2? 0 times B1 plus 1 times B2. Okay, so you are actually checking where B2 have to go. So B2 have to go where? 4C1 plus 7C2 minus C3. And then you apply coordinate vector on with respect to C on 4C1 plus 7C2 minus C3, you also get 4, 7, and minus 1. So let's write down. So if I apply this on E2, what do I get? First of all, I should get B2. Okay, how should I get B2 here? Actually, maybe let's show you how I get it. Maybe that's better. So 0 times B1 plus 1 times B2 equals to this function apply on T of B2. Okay, in this case here, what do you get? By question, you should get 4C1 plus 7C2 minus C3. Okay, but if you read this out, it's just 4, 7 minus. So in other words, if you put this together, M is equal to 3 minus 2, 5, 4, 7 minus 1. And actually, there's an easier way to read this solution. It is just equals to T on B1 with respect to C, and then T on B2 with respect to C. Okay, yeah. So I mean, in real calculation, you just apply this formula. Okay, you just apply this formula. Okay, no need to do this long thing. Why I want you to do this long thing? I want you to appreciate how we figure out this TB1C. Okay, does it make sense? Okay, so I mean, there's a comparison here, right? Okay, so there's a comparison here. So you still need to copy, or can I move? I'll give you the solution anyway. So let's go back to here. So let's compare. Let's compare what we had before and now. Okay, so this one is before. That one is after. Okay, so after, what do we have? We have T from V to W, such that V is dimension n, and then W is dimension m. Then there exists m by n matrix. In this case, we call it. Let's also call it A. Okay, let's call it A. A, such that the call it vector on Tx with respect to C. Okay, so we should tell you what is C here. So C is the basis. So W have basis called C, and then V have basis called B, equals to A times the coordinate basis of X. Can you see the similarity between these two? Okay, I won't tell you what is A, such that A is equals to, okay, let's put it nearer so that you can compare. So A in this case will be equals to T, T of B1. Yeah, T of B1 in C, and then T of B2 in C, up to T of Bn in C. Okay, can you see the similarity between these two? First of all, we abstract the idea of Rn and Rm. Okay, we go to general vector space. And then after doing this general vector space thingy, right, you see, inside this matrix A here, we need to consider not just vector itself. We need to consider the coordinate vector. Okay, why? Because we need to bring our abstract vector space back to Rn and Rm. Okay, but you see the configuration is the same. You still apply T to the basis of your codomain. Your domain. Okay, you see, in the previous A, you apply to E1 up to En. This is the basis for Rn. But now your basis for V become what? B1 up to Bn here. Okay, and then Not enough, huh? You need to read this TBI in terms of the basis C. Okay, otherwise your element will be some abstract vector inside of W. But we just want Rm. Okay, we want Rm. So we need the coordinate vector. Okay, so another thing is about these two things here. Okay, so previously you just have Tx equals to Ax. But now in this case, your Tx and X need to be read using the coordinate vector first. Okay, yeah. You need to be read until with a coordinate vector first. Why? So that you live in the right vector space. So Txc is living in Rm, and then xb is living in Rn, and then the matrix here is m times n. Okay. Does it make sense? Okay or not? Okay. So a little bit complicated when we go to abstract vector space. A little bit. Okay, where you need the help of your coordinate base vector. Actually, you no need to guess one. If you are applying t onto your x, the coordinate vector you should use is obviously on w1, which is c. Okay, if it is just x, you need to consider the v coordinate vector in v. Okay, no need to guess one. Okay, you need to know where your vector live in this enough. Okay, does it make sense? Okay, so you see, the term that we had before actually is a special case. Can you see it's a special case here? What's the special case? You can take your B and C as your standard basis. Okay, if you take your B and C as the standard basis, you don't need the bracket anymore, right? Still remember last time we say x is equal to its coordinate vector in the standard basis. Okay, so if you take B and C as a standard basis, this is exactly what you have here. All the coordinate vector disappear. Okay, does it make sense? Okay, what time is it? Okay, very good. Let's see. I think we got example. More example. Let's try. Let's try one more example. Yeah, let's try one more example. Can I give you try one more examples here? So let's try this example. No need to show this is a linear transformation. This one I already showed it for you already. Can you recognize what's this linear transformation here? A0 disappear, and then the t for A1 disappear, and then 2 become a scalar of A2t, and then the t reduced by 1 degree. Can you recognize what's this? Anyone recognize what's this? What's t here? Differentiation. Good, very good. D over dt. This is actually differentiation. Last time I proved to you already, right? I give you this solution. Okay, so try now. I ask you to find this TB here. So what's this TB? I will tell you this notation. So this TB is a special notation for your M if your domain and codomain is the same space. Okay, so we call it TB. Why TB here? Because we also fix the basis. Both sides have the same basis. Okay, in principle, we can change basis, right? Even for R2, we have different bases. But in this case here, both domain and codomain use the same basis. Okay, yeah. So try do this. Try and find this. So maybe I give you a hint. So what's the formula we had just now? TB should be equal to what? T apply on B1 written 2B. So here is a B written in the basis of B, and then how many bases here? So you are P2, right? So P2 is dimension what? What's the dimension of P2? Still remember? 3. Okay. Actually, you can write down the span, right? Okay, they write it for you already. Yeah, so they write it for you. So this is your span. Yeah, so you have dimension 3. Good. Okay, so you need to do TB1 with respect to B, TB2 with respect to B, and then TB3 with respect. Okay, so try compute this. Compute this 3 vector here. Okay, compute this 3 vector. We done last time. Let me try and compute this 3 factor. Okay, let's go through. So what is your B1, B2, B3 here? So B1 is 1, is given by the question. And then B2 is T. And then B3 is T squared. Okay. So what is T1 here? You differentiate 1, what do you get? You get 0. And then differentiate T, you get 1. You differentiate T squared, you get 2T. Okay. So now the problem is how you read this polynomial in terms of beta. Okay. So before that, okay, let me write down the full step for you how to read this. So how to write 0 as a linear combination of 1t t squared. 0 times 1 plus 0 times t plus 0 times t squared. 1 ne? 1 times 1 plus 0 times t plus 0 times t squared. 2t eh? 0 times 1 plus 2 times t plus 0 times t squared. Okay, so if you read out the scalar, what do you get? So the first one, what's the scalar here? 0, 0, 0. Second scalar, 1, 0, 0. Third scalar, 0, 2, 0. So this is your matrix. They call it a B matrix, beta matrix, or the matrix for T. That's all. So this is your matrix. You know what this matrix can do for you or not? Do you know what this matrix can do for you? Okay, so let me draw the picture again to keep your memory good. So we have this T here, and then we have A plus bx plus cx squared. And then if we go through this T, this polynomial will become B plus 2C x squared. Okay, but we also know that there's we call it isomorphism. Okay, P2, there's a coordinate vector mapping. Okay, from P to R3, both cases. And then this matrix is hanging around here. So let's see what this matrix is doing the job we want it to do or not. Okay, so what does this matrix do? Let's say if you have a polynomial a plus bx plus cx, this guy here should go to, okay, let's use a green arrow for elements. So let's use this green arrow here. Then use the blue arrow for the spaces. Okay, so if we go down this green rock, right, we should get A, B, C. Okay, if we go down this green rock, right, we get 0, B, and 2C. Okay, what we want to do is, what do we want to do? We want to close this loop. We want to make this two paths equal. Okay, is it equal or not? If I multiply by this matrix here. So if I multiply this matrix, is it equal? Let's multiply it. So 0, 1, 0, 0, 0, 2, 0, 0, 0 multiplied by A, B, C. What do you get? You get, oh, am I right? Wrong stuff here? Oh, yeah, okay, sorry, here is wrong. So B plus 2x, right? 2cx. So B 2c, and then the coefficient for x squared is 0. So here is 0. Okay, so let's see. So if you do matrix vector multiplication, we should get B first one. And then second one, we pull the C out, multiply by 2, and then 0. Okay, so it's equal. Does that make sense? Okay, so two rows were equal. Okay, so the key here is, you see, I define T on polynomials, but there is an associated matrix. Okay, what does this associated matrix do? If you apply coordinate vector mapping to your vector space, and then this matrix will get you from the domain Rn to the codomain Rn, where this Rn and Rm correspond to the abstract domain and codomain, abstract vector space. Question? Any question? Any question? You want me to repeat? Question? Okay. So far, so good. Okay. The next part, before we end out this section, we want to understand the change of basis. Sorry, we want to understand the diagonalization using this context here. Okay, let's understand the diagonalization using this context. Okay, so what's this question asking? So if it is better for you, I think we will draw the picture. So we have a linear transformation defined by this matrix multiplication. Okay, sending x to ax here. Okay, now let's ask you to find the basis of R2. Okay, such that beta matrix for T is a diagonal matrix here. Okay, so so although they haven't tell you what is the basis for R2, right? We just start with the standard basis. Okay, actually they assume we start with a standard basis here. Okay, now the problem is they want you to change basis. Okay, you want to change your basis such that the B matrix for T is a diagonal matrix. Meaning what? You need to form your D here. Okay, such that it represents this transformation. Okay, such that it can represent this transformation here. What to do there? To do here. Okay, the question is you need to find appropriate. So let me put here. So what's the B you need to put here? What's the B you need to put here? Such that if there's a arrow going between this square here, this D should be diagonal. So well, so you should at this moment you should think about diagonalization already. Correct or not? You should think about diagonalization. What does diagonalization do? If A is diagonalizable, A equals to what? P D P inverse. You start with a P inverse, right? Okay, you start with a P inverse. So A equals to, sorry, okay, let me write down. So A equals to PD P inverse. Okay, so let's see the arrow here. A is going from here to here, right? So you should put a P inverse first. So meaning what? Actually, maybe you should go this way first, right? If P is going this way, then P inverse is going the other way. Correct or not? Does it make sense? Okay. P inverse going the other way. Okay. Let's write. Let's draw the other arrow. So if P going out, P inverse surely go down. Okay, this makes sense. Okay, so P inverse D and then P. Okay, that's right. P is going up. So this is the picture you have. Okay, so what does it mean here? Actually, your diagonalizable is how to say, one of the uh, how to say, what do I want to say here? Oh, okay. So one way to think about the diagonalization is to think about change of basis of R2 here. Okay, change of basis of R2 here. Yeah. Okay, change of basis of R2. So let's try work this out. Let's see if we can work this out. Okay. Right. So if we use the logic here, right? If we use the previous logic, so the diagonalization. If you have any problem, feel free to ask. Feel free to ask. Just ask only. Okay. Okay, just ask. 不要，好像不好意思这样，你就问吧。你觉得哪一个 part 如果觉得很怪，问吧。Yeah. I mean, the purpose you are here is to ask. 对吧？问吧。如果你觉得哪一句话很奇怪，just feel free to ask. Any question? Tonight. Can you follow? If you cannot follow, I think most of them cannot follow. Can you follow? No. Okay. So which part you think is stuck? No, I mean we need to start from anywhere. I mean any start point. Anything you think that doesn't make sense here? Which part? I mean one of your answer can say every part, but we need to start somewhere. Okay, that's the point. Yeah. I want to try. I give you a chance. Huh? Or do you understand? If you don't understand, surely there's one part you don't understand, right? Or maybe we can try. Okay. So listen to my question first. Listen to my question first. Okay. So after you read this question here, do you know how to draw this picture up? No, right? Okay. How about drawing the first part out? Yes, right. Okay, this one makes sense, huh? Okay. After drawing this part out, you should draw the second part out. Based on what question says. Correct? Because this question says that find a basis of B, find basis B R2 such that there's a matrix with respect to this T here is a diagonal matrix. So you have a diagonal matrix between two R2 with a different span of basis. All right. Okay, this two arrow is just following what this question says. That's all. Okay. Now my job is to create the extra two arrow here. How to create this extra two arrow? This is the problem. Okay, so I try to link this problem back to what you know about matrix and diagonal matrix. Correct or not? When you have a connection between a matrix and a diagonal matrix. This is what we learned in the previous section, right? When A is diagonalizable. Okay, when A is diagonalizable, then there exists a P such that PD P inverse equals to A. Okay, now I try to argue that actually this P will form the bridge between these two arrows. That's all. I haven't shown it to you, but I'm like, we try to figure out the truth. Okay, can follow? So far? Got question or? Question? No? Okay. How about the rest? Yes.
Let's start with P first.
Okay. So well, I mean, if you're gonna apply A to some x, right? Shouldn't you do P inverse x first? No. You should do the leftmost first, right? Like function composition. Fg, you need to apply G first and then apply F. Alright. Yeah, this one is actually a very important question. This one is very important. A lot of students confused. Okay. Anything else? Can I ask? Can or not? Question? Other question? Can make sense of this square here? Question? Okay. So what's the next step we should do? What do you think? What's the next step? We need to diagonalize this matrix. Okay, so diagonalize this matrix. So diagonalize. Okay. So to diagonalize A, you start with your characteristic polynomial determinant of A minus lambda I. In this case here, you should get 7 minus lambda times 1 minus lambda plus 8, right? And then if you factorize this, you should get lambda minus 5 and minus 3. Okay, then second, you should find your eigenspace. Okay, so for lambda equals 5, we get A minus 5i. You should get 2, 2 minus 4 minus 4. Very nice matrix here. Or if you row reduce this, you get 1, 1, 0, 0. Okay. Then what's the eigenvector you can pick here? You can pick it as a span of minus 1 and 1. And similarly, you also find the eigenspace for lambda equals to 3, okay, where you also get nice matrix here. 0, 0. And then this span here is minus half and 1. So in the end, what's your P here? So you should take your P to be, you can take your P to be minus 1, 1, and then your minus 1, 1, and then the other one, what do you think? You can scale it if you like. You can get minus 1 and 2. Then your D is 5003. That is. Yeah. Okay, so so you found that this is your change of diagonal matrix, but how do you find, how do you what's the B then? What's the B you have to pick, choose here? What's the B you need to choose here? What's the B you need to choose here? In this case. The B you need to choose here. Don't say it. 50. What's 50? Oh no, this is already is your D. This is the um this is your this is your diagonal matrix. Okay, instead you should play around with your P. Okay, so the claim is this B here should be minus 1, 1, and minus 2, 2. Okay, such that then you will replace this P and P inverse by your coordinate vector. What's your coordinate vector here? Your beta. Yeah, you should check this error commute. We said that if you go down the two root, it's the same. We say this square commute. You want to try? I think I should convince you. You guys don't seem too convinced. Okay, I think I try for you. Okay, let's try this. Okay, let me see how I check this for you. So let me prove to you how it works. Okay, I think this part is pretty important. After we prove it for you, this part, and then we will break, and then you take quiz from here. We will discuss quiz. Okay, so let's check whether this thing works or not. Okay, let's check how this thing works, and then I think it will explain why I draw this kind of rubbish thing here. Okay, so let me everything away. Then we try to check what we are doing here. Okay, right. So what are we gonna do here? So we're trying to check whether this diagram commute or not. So how to check this diagram commute? There are two ways. Two ways to reach from R2 to R2. So one way, we either go this way or we could go this way. Agree? Yeah, okay. So there are two ways here. So let's compute the two-way. The two-way should give you the same number. So we should check it for every vector. Okay, so let's start with any vector here, x and y. So if I do D on x and y, and then we do this, it should be the same. Wait, it should be the same as, hey, this one is path 2, huh? Okay, this one throw to path 2. How about path 1? What do we do first? We do the coordinate mapping first, and then we do A. Okay, these two should agree. Okay, we follow this two arrow here. Okay, and then if I apply, which one we going to compute first? Let's compute this guy first. Okay, let's compute the first root first. So if we read, if we read this vector, let me think. So how should we read this vector here? This vector is written as a span of these two things. Let me think. How should we talk about this? But let me think. How do we think about this? So this is our P. This P here. Oh, okay. I think we cannot show. Oh, if this one is P. AP was B. Okay, wait. So let me think about this first. So if we go down, the first root is PA, and then go down, the other root is DP. And this is just what we computed. I want to show you about basis. Let me think how to show you this. Okay. Can you give me 10 minutes break? Let me compute, and then next hour I'll show you. After I compute, I'll show you. Okay. Now you can take back your quizzes, and then you take a photo. Okay, and then we will discuss also in the next hour. Not next hour, maybe 45 minutes. Okay, let me compute this thing. I show you how powerful is it. Okay, let me organize a bit. Then I'll tell you how powerful is it. Okay. Now you can take your quiz first and then take a photo. And then after that, you return it to me. Can you help me to jaga? Okay. One person take one. Cannot take for friend. Okay, so if you want to take your quiz, come and get from Amber here. Amber. Okay. Yeah, let's break until 5:34. Okay.
Thank you.
Okay. Yeah, yeah. 等一下我会给答你的评论。 哎，哎，
为什么
啊
是这个方向是 P inverse，然后这个方向是 P？就是它不是这个到这个可以是这条路是 A，
对，
然后或者是这一条路，这条路的话，那不就应该是 P，然后 D，然后 P inverse。
其实看你怎么教这个 P inverse 吧。但是如果我们是把 A 已经是写成 PD inverse 的话，一定是先做 P inverse 嘛。所以就是先走这条路，看你怎么走啊。
P inverse。
没有啊，这个就是function composition 的顺序嘛。就是
这个是最内部的。
对，
这样吗？
对，反正对，没有。现在我在想一下，这个东西到底做了什么事情呢？我现在忽然间卡住，我再想一下怎么去用这个，怎么去用它。I mean 算是算得出来，但是只是说怎么解释这个 beta 到底做了什么事情。在想着。因为我记得我上次的答案好像少了东西，其实我没有把 beta 写出来，我之前答案，然后我也没有解释这个 beta 做了什么事情。想一下，我有没有写？
接下来
可以。Hey, yeah.
This is the total is full or
No, just only two. Only
just
two. Yeah. Later I'll discuss if you think that.
Yes, just
Yeah, sure.
I think
Hey, where are you come from? Where are you come from?
Tunisia,
Tunisia.
Tunisia,
Where is it?
in the north of Africa.
North Africa.
Yeah.
Because your style like a bit similar to one of the way of speaking. I was suspecting he is also from there.
Yes,
But he studied in France. I'm not sure where he came from. Maybe I should ask.
yes, because Tunisia is near the Europe.
Europe?
Yes.
Okay.
So the accent is like similar.
But I think he just studied there, but I'm not sure which part. I mean, where he came from. Maybe I can ask.
Okay, thank you so much.
对，等一下我会讨论。这是错的吗？对，他是错的啊。
这个是因为没有 bracket。
对，没有 bracket。
好
等一下，我会讨论。
要 bracket。
要 bracket。是想不到，卡住了啊？Yeah。Transpose。哦，对。等一下我会讨论。
这个 basis 我想判断，
哎
不是两个条件吗？
对，
然后我们就是有刷题刷到一题，它的解析是 只要算出 determinant 就可以
哦，OK，对，
考试可以。
也可以这样做。这个其实是 invertible matrix theorem 来。哎，
解出它的算出它的值，然后直接，所以它
可以这样，
又 span 又 linear， 可以直接这样做。
可以这样说，但是你知道为什么吗？
Not equivalent to adding.
对
So every period, every column and every.
对，没有错。
要把这个也说进去。
不用了，只是我想要。
就是算出值，然后直接得出结论。
其实是 IBT 的其中一项。我们没有强调，因为太多东西要讲。但是最基本的我一定要让你知道，就是那个 basics 你可以用这些解法，但是就是
感觉这个有时候比较快。
对，是比较快，是比较快。对，但是你进到那个 basis 跟那个 span 的做法其实你有发现吗？其实就在做这件事情嘛。对呀，其实就是在做这件事情。
有问题。
这个不是说它可以是这样子的，也可以是化简之后的。那如果
等一下我看一下，
它可以是化简完了，也可以是这样。
是我是不是看错？可能我看错啊。OK， 等一下你过来给我讨分，因为可能你还有其他分要。
对。
Okay, so please take a photo and then don't write anything on it yet. I think we resume to this question again. Example next lecture. Let me think how to talk about the significance about it. I suddenly stuck on it. Yeah. Oh, okay. Later you come back. Yeah, sure. So please take a photo first. Don't write anything on it. Please don't write anything on it. And I think next lecture I will explain in full what is this question is doing. Okay, no? Is it okay? Yeah. Let me go back and think about. Suddenly I stuck on how to see what is going on. Okay, then let's discuss quiz then. Let's discuss on the quiz. Okay. So for the first quiz, I think it's straightforward. You find inverse for your matrix using the elementary row operation. So you set up AI. Okay, so you set up your AI. Okay, after you set up your AI, you row reduce your A to I, and then what's left over is your matrix. So one thing I want to talk about is you have a lot of calculation error. Okay, you have a lot of calculation error. So make sure that every step you do it slowly. Okay, do it slowly. Okay, don't rush. And then how to check whether the end part is the solution. How do you check? What can you do to check? You should take your A inverse multiply with your A. See you get help. Okay. Final mark is 2. If you don't get this final mark here, depend on how severe is your mistake. Some of you just wrong 1 spot, 2 spot like that, or some of you wrong every spot. Okay, so as long as you know how you need to get to this identity matrix here, then you will get this step marks. Obviously, need to be supported by some row operation. Okay. Yeah, and then if you know that you need to start from this, but you don't know what to continue, maybe we just build 2 marks. Okay. Yeah. So far, okay, no question 1. Got problem? Yeah. Okay. Okay, question 2. Okay, question 2 is finding a null basis for null space, column space, and row space. Okay, obviously you need to row reduct it. So after you row reduct, you found 2 pivot position here. on two pivot position. And then, so how to figure out the null space? So null space is the number of free variable here, so correspond to this two free variable. So you need to, if you want to find the null space, you need to write down the general solution. Okay, and then check that your general solution is spanned by two vectors. So these are those who didn't come today. Okay, so next, about column space. So column space will be the column that correspond to the pivot position here. Okay, I think it's very good. I think only few of you pick from this REF column. Okay, less than 10, I think. Okay, so make sure that you know that you need to pick from the original matrix here. But for row is different. Row you can pick from the any row with the pivot, but don't pick the same row. Like you don't put the same two. I mean, if you're gonna pick this 0, 1, 5, minus 6, don't pick 4, 5, 9, minus 2 again, because they how to say, I mean, dangerous, a bit dangerous. You know what's the dangerous? Why is it dangerous? Because they might be, how to say, scalar multiple from each other. I mean, well, you should pick two of them from the same, how to say, same matrix. I think I saw some of you pick one from one matrix like this. It's very dangerous. Okay, because you're not sure whether they are scalar multiple of each other. Because already after several times of a row reduction, quite dangerous. So my advice is, if you're gonna pick row vectors, you should pick from the same matrix. Okay, from the same matrix, it's definitely linearly dependent. Okay, if you pick from different stage of matrix, then it could be a risk that they are linearly dependent. Okay, yeah. So make sure you pick from the same matrix. Other thing is you guys don't put bracket. Okay, you don't put bracket when you mention about basis. Okay, you don't put bracket. Another thing is when you write row vector, right? You roll like this. So where's the row vector answer? So you roll like this. Okay. So the question I want to ask you is, did we write R4 vector like this or not? No, we don't write like this. Okay. One way you can go around with it is you put a transpose here. Okay, if you put the transpose, this one, then it will become a column vector. Yeah, this is the notation we use in the class, in the lecture note. And then some of you didn't write basis. You don't say basis. Okay, you just say now A is these two. No meaning one. Now A is not these two vectors, it's the span of these two vectors. Okay. All the linear combination was satisfied. Okay, so basis is a set of the two vectors here. Yeah, so make sure you write down basis, write down this bracket. Okay, any questions so far? Any question? Okay, if no question, let's proceed to the last one here. Okay, find the coordinate vector. This with respect to the basis. Okay, so most of you start from scratch. You just cook out the augmented matrix here. So you want to try and find the linear combination, right, between these two vectors, such that you get 6, 9, and 8. Okay, so you solve this, which is okay. Another way is you notice that I think you do this kind of row reduction in question 2 before. Okay, so you can use the relation here. But if not, you just do row reduction. Yeah, I think this one is, I mean, most of you got marks from here. Question 3, quite straightforward. But there's quite one very funny answer. You write a English word inside your vector. I don't think it makes sense because 3 is not a real number. Out of any number you put here, please don't put an English word here. Okay, no? Because 3 is not a real number. Okay, so 3 is not a real number. Yeah. Okay, you can put anything, but please don't put a real number. Okay. Yeah. So you should see that if you found the coordinate vector in R3, there's a problem, right? Because your basis only have 2 vector. So this guy should live in R2 actually. Okay, you cannot live in different spaces. Okay, so it should be something wrong already. Okay, some of you write -450 or something like that. Yeah. Okay, live in a different space. Okay, any questions so far? Question you want to ask? Okay, so the full answer that I want to say is called 百家宁. Is 百家宁 here? Yeah, you. Okay. Are you okay if I post your solution to the Moodle? I scan your solution and post to the Moodle. Yeah. So all of you can refer to her solution. Her solution is very complete. It's almost the same as the marking scheme. Okay, so it's not the same as marking scheme because marking scheme didn't do checking also actually. She did checking. Okay, she did the checking and then she give all the possible, like not all the possible, but at least what we mentioned before, the 2 possible way to choose row space. And then this one easy to check, right? Just check this. So this is your checking actually. This is your checking. Have time to do all. He did everything. Yeah, she good. She get full marks. Which program you are from? MBT Marine Biotech. Okay, you are the future of your program. You are the future of your program. Yeah, I hope my MAT also can do this. Very few people can do like this level. Okay, let's see. This time around, got who is the high achiever? We got Yahan. Where's Yahan? Yahan. Okay, good. Seng Jie, very good. Seng Jie got a lot of improvement. Hamdan, maintain. Hamdan. Yeah. Mingzhou, I think somewhere at the back, right? Ke Jin also got very good improvement. Yiling also, Hong Yiling, good. Hui Yue, I think Hui Yue didn't come, right? Hui Yue come, no. Zijun, Zijun here, yes, good. Fang Ling, good. Let's see, Ruoqi, good. Yokting front, right? Yokting here. Luinichi, also good. Faturaman, good, very good improvement. Siteng, the front. Jianing, mentioned already. Jiayi, okay, good. Oh, side by side, very good. Friends influence friends. Yishen, okay, Yishen, good. Wucheng, Bai Wucheng, okay, good. Yang, okay, this one usual, maintain. Yuan, the front right, maintain. Good. Sanai also very good. Yeah. Okay, so try to revise. Okay, if you don't understand, you can message me, email me, or ask me. For the example just now, let me try and go back, figure out. Okay, somehow I get stuck. Lecture also can get stuck. What do you think? So you get stuck is very usual one. Okay, so but the problem is, what is the problem between both of us? I mean, difference between both of us is we will unstuck. Try to do unstuck. Okay, so usually students are my student. They stuck, they just do something else. They won't continue and work on it already. They give up. Okay, so why we can study up to PhD? Because we don't give up. If we give up, we don't do PhD anymore, right? Or not. So the only difference is please don't give up. Okay, yeah. So I'll show you. I'll show you next lecture. Okay, how to do that example. I mean, we already do the example, but I want to see what's the significance of what we are doing there. Yeah. Okay, any question so far? Wow, today got a lot of time. So what's left to done? What's left to do here? Let's see what's left to do. Maybe we can organize a bit. Let's see what's left to do here. See, we got time. Okay, we have chapter 6. So chapter 6, what's left to do is chapter 6. After that example is finished, and then we'll move to chapter 6. So chapter 6 is about orthogonality. Orthogonality meaning 90-degree to each other. Orthogonal. Okay. And then we will introduce what's the inner product. So you from the word, you should think about new kind of products. Okay. And then we talk about length, and then orthogonality. So the angle between two vectors. And then next, I will tell you what is the orthogonal set. So orthogonal set means everything, every vector inside that set should be 90-degree to each other. Okay. Although we put here the dot product is 0, it's actually 90-degree to each other. And then we will form something called orthogonal basis. So meaning what? We know basis, right? Linearly independent and span. But now we have extra condition. Between every two vector must be 90-degree. This is true for your standard basis, right? You recognize your xy plane. They are 90-degree, right? X, Y, Z also 90-degree to each other. Yeah. Okay, so they are orthogonal bases. And then we do something called projection, orthogonal projection. So we want to project on these orthogonal space. And then what else? Yeah, orthogonal projection. And then Gram-Schmidt. Okay, Gram-Schmidt is you start with a basis. Okay, you want to make it into orthogonal basis. Okay, so from a basis, we can always construct orthogonal basis. Okay, I mean, when you start with a basis, you only know they are linearly independent, they are span. Okay, but you don't know, I mean, they might not be 90-degree to each other, but you can make it into basis that's orthogonal. So this is Gram-Schmidt. And then solve this least square problem. Okay, least square problem is we want to solve AX equals to B, right? But let's say your system is inconsistent. Cannot find solution. But we can find a closest solution. This is called the least square problem. Okay, we can use this least square solution to approximate the solution. Although we know that there's no solution, but we find the closest solution. Okay, so least square problem. And then the generalization of inner product, so inner product space. And then that's all, finish. Okay, we won't do chapter 7, but if we got time, we will roughly say what chapter 7 do. And then if got time, we also will discuss some question. Okay, some question. I think that will be last lecture. So during the last lecture, I think you can bring your question come here also. For example, what kind of question you can bring? Because my tutorial question didn't cover all the tutorial, right? So maybe you can request to do some question from textbook that we didn't discuss or I didn't give you the solution. And you don't know how to do or you want to check. Okay, then on the last day we can do this. No? If not, maybe I come up with some question we can discuss. No? And then will be that's all from this semester. Okay, know how to finish this semester? Okay. Okay, it's very quick. A click of my finish already. Okay. Yeah. Do you know your timetable yet? Not yet, huh? Maybe next week. I think next week they will release. Yeah, next week. Okay. So far, any question? Okay, if not, maybe we break earlier today. So please return your quiz. Yeah. Thank you. Hey, hi. Something.